Welcome everyone to this lecture on the topic of laws of motion. So in the last video we were doing questions on the topic of constraint relations and pulley block problems. So we have been covering the constraint relation problems for a last 2-3 videos at least. So now we'll be moving on to some different types of constraint relations which can be asked. So let us begin. So the first constraint relation which we studied was the pulley and block constraint. So this constraint relation is the second constraint which we are going to study. That is the second constraint relation. So this one is the rod against a vertical plane constraint. So what are we trying to study actually? So let us draw a wall. So this is the vertical wall which we are talking about, and we have a horizontal floor. After that, let us draw a rod indicated by this red line standing on this wall, leaning on this wall. So we'd say that this wall is particularly smooth, and this rod is standing on it or leaning on it. So what are we trying to evaluate? So we are trying to evaluate the velocities of point on the rod. That is, this is the rod which we are talking about, and we want to find the velocities of the points on this rod. So to find those velocities on the rod, we have to remember a simple idea which will be used many times, not only in this particular case but in other cases also. So what is that idea? So that idea I briefly stated when we started the pulley block constraint, but we didn't discuss it. So the idea which we are talking about is that, let's say we have a rod like the rod which we have drawn, then no matter, we can take one more rod to understand the idea which we are going to discuss. So whenever there is a rod and it is moving in space, it is traveling in space, it is rotating, it can rotate about some points, random points. So whatever the case may be, if the rod is rigid, then that means that if we consider 2 points on the rod, let's say this point is some A and this point is some B. So we have 2 points on the rod, and we are considering the velocities of those points. So let us say the velocity of point A is some VA vector. Let us give us some random velocity at this point, and the velocity of point B is some VB vector. Then the rod is rigid one, right? We know that the rod is a rigid rod. So it would mean that the distance between the points A and B, that is the distance AB. Remember what we are talking about. We are talking about distance, not the position vector. The position vector of B as seen by A would change. As you would be imagining, the position of A would change and position of B would change. So the position vector of B with respect to A may change or may not change. But what we are talking about is distance, the distance AB. So the rule which we are going to remember, or the idea which we are going to remember, is that whenever we have a rigid rod and it is rotating or it is moving at some velocity, like in this case it is going to fall on this wall or fall along this wall, then the velocities of point on the rod, that is these 2 points A and B, the velocities of points A and B on the rod, and that is these 2 points are on the rod, along the rod. That means the components of their velocities along the rods. So let's say the component of the point A along the rod is some v1. Let's say its component is some v1, and let's say the component of velocity point B along the rod is some v2. Then by the idea that this rod is a rigid one, that means that the distance between the points A and B cannot change. So since the distance between points A and B cannot change, that means at this instant of time, whatever velocities we have drawn of point A and B must remain same along the rod. That is, V1 should be equal to V2. Now what this does is that this ensures that the distance between the points A and B does not change, because how much distance the point A has travelled along the rod would be same as the distance which B has travelled along the rod, and this is because of the fact that they have the same velocities along the rod. Remember that we are not saying A and B have the same velocities, because that would mean that their velocity vectors are same. We are not saying that. We are saying since A and B lie on a rigid rod, that means that the velocities of point A and B along the rod, which we had considered unequal initially, V1 and V2, have to be equal if the distance A and B is not to change. So we say that the rule becomes velocities of all the points on the rod along the rod are to be equal. That is, these velocities V1 and V2, they have to be same. So this is because the distance AB has to remain a constant. It is a rigid body. So how do we apply it? So let us see how we are going to apply it. So like this case, the rod is which is leaning on a wall case. We are usually given the velocity of one of the points on the rod. Let's say we are given the velocity of this point, the bottommost point. So we are given the velocity of bottommost point on the rod, as is given in this figure. The velocity of point B, that we know. That this velocity point or this point's velocity is some B. And let's say the rod is making some angle theta with the horizontal. So it is making this angle theta with the horizontal. So we have drawn this. This angle is theta. So this angle is vertically opposite is theta. So we know that the point B would be moving along the floor, right? As the rod slides down, you can imagine that point B would be moving along the floor. Same thing can be said for point A also, except that for point A we do not know its velocity. We do not know what is the velocity of point A. Let's say that velocity is some V dash. So we know VB, we do not know velocity of point A, and that is what we have to find using what rule we have learned. So we have learned that the distance of any 2 points on a rigid body, that is a rod, cannot change. So the velocities of points on this rigid body, which is a rod, have to be same along the rod. So okay, let us proceed. So how would we apply this principle here? So we know this angle is theta, this is a right angle triangle. This means that this angle would be some 90 minus theta. So now we know that the idea is that velocity of point A along the rod, which was chosen as V1, would be equal to velocity of point B along the rod, which was chosen as V2. Can we find these velocities in terms of V and VB? So let's say this angle is alpha, let's say this angle is some beta. So it say the component of VA along the rod would be VA cos alpha at this instant, and this should be the component, this should be equal to the component of velocity B along the rod, that is VB cos beta. Let us apply this equation in the question which we have. So the velocity of point B along the rod. So what is the direction which we say along the rod? So this is the direction which we are saying along which is along the rod. So the component of point B's velocity along the rod would be this V cos theta, right? this component would be perpendicular to it and this component would be along that rod. Similarly, we can say that velocity of point A along the rod which would be v dash cos 90 minus theta. So from this we can easily say that v cos theta divided by sin theta is equal to v dash, or v cot theta is equal to v dash. So this is the unknown velocity which we are trying to find. That is what is the velocity of point A if the velocity of point B, which is touching the ground, is known. And remember that both these points are on the rod. They are on the rod and they are in contact with the ceiling and the floor respectively. So that is what we have done. Okay, so now let us apply this idea in more cases. And again, this equation is pretty important, as you will be able to see that VA cos alpha is equal to VB cos beta, and this basically illustrates the same idea and it comes from that idea. Okay, so this is what is the rod constraint. So now the question which we have is you have to evaluate the velocity of midpoint of the rod AB. We have the same system AB, right? The same system AB. What is the velocity of midpoint? So we have chosen some midpoint of the rod and we have to find its velocity. What would be the velocity of that midpoint? This looks horizontal, but it would be in some random direction. So what is this velocity of midpoint vector that we are looking for? So how do you think about it? So what we can say is that we know at least 2 points velocity on this rod, that is the velocities of endpoints, but that is not helping us directly in finding the velocity of midpoint. Where would the midpoint be? It would be at some location. If I can select the velocity of midpoint with some value, let's say its value is some v m, and let's say it makes some angle, let's say alpha or beta. So we would get two variables, right? And it would be quite difficult to evaluate two variables if we have a single equation only. So what we'll be doing is that let us take the x coordinate of this midpoint M and the y coordinate of this midpoint M, and we know that M is the midpoint of this whole line, right? So if this line which we are talking about, it is making an x intercept with the x axis, let's say this intercept is x, and let's say it is making some y intercept with the y axis, then the position of the point M would be x by 2 I cap plus y upon 2 j cap. So this would be the midpoint of the position, right? So we have found the position vector, right? Can we find what is the rate of change of x? So rate of change of x is the velocity of point B, right? Because the x point is where B lies. So and we know what is the rate of change of the velocity position of B, and that is the velocity of B. The velocity of B is V, that we know. So that means that dx by dt simply becomes V. And in the same way, can we write dy by dt, as y is the y coordinate of the point A and how it is coming down, and that is represented by v dash. So we know v dash is a positive quantity, so we write that dy by dt is some minus v dash. So to represent that y is decreasing with time, and we know v dash is this v cot theta. So it's a dy by dt is equal to minus v cot theta. So what this has done is that this has eliminated the need of two variables in finding the velocity of mass m. Otherwise we would have needed the variable its velocity and its direction. So instead we have taken x and y and we have solved in that terms. So if we differentiate the position vector of the velocity of the point m, then we'd get the velocity of a point m. So that velocity would be half dx of I dt I cap plus dy by dt j cap. So from this you would get half v I cap minus v cot theta j cap. From this we can take v common, v by 2. So this would come out to be minus I cap minus cot theta j cap. This is the velocity in that point. So in this particular video we learned how to find the rod constraint and how to apply in the cases when rod is sliding on some wall, or to find more information about the points of the rod. So in the next video we'll be continuing with the wedge constraint and the rod kept on a hemisphere constraint. So in this video we'll be covering until up to this point only. So thank you for joining and have a nice day.